Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on June 30th, 2025, just 2 days ago. This paper introduces a new method for cleaning up noisy depth sensor data that reduces errors by at least 37.9%. The paper is titled, Consistent Time of Flight Depth Denoising via Graph-Informed Geometric Attention. And as we'll see, the results are not just better on paper, they look much cleaner too. The authors tackle the challenge of denoising data from these time-of-flight sensors, a key problem for robotics and augmented reality. Alright, so to see this in action, the authors provide a great visual comparison. First, we have the ground truth. That's the perfectly clean, ideal depth image they're trying to reconstruct. Next to it are 2 frames of the actual noisy sensor data. It's pretty messy. Then we see the results. A previous multi-frame method, MTD-net, blurs out details like the teapot, but the proposed GIGA-ToF method, which stands for Graph-Informed Geometric Attention, successfully removes the noise while preserving sharpness. It does this by focusing on the underlying relationships between pixels, which don't change even when the object moves. So, how does it achieve this? This next diagram really shows the core idea. The model builds what's called a graph for each frame. A graph here is like a network map, where each pixel is a point. The strength of the connections between these points is stored in what's called an adjacency matrix. The key innovation is cross-frame graph fusion. The model intelligently maps the structure from the previous frame's graph onto the current one. This process updates the current frame's adjacency matrix, preserving the underlying geometry of the scene, even when things move. Building on that idea of graph fusion, this network diagram shows us the complete GIGA-ToF pipeline. Okay, so on the left, 2 consecutive noisy frames enter the system. They first pass through a feature extraction network, shown in blue, to pull out key geometric information. Then, this information feeds into the core component, the yellow Giga module. This is where the cross-frame graph fusion happens, intelligently combining the underlying structure of both frames. Finally, the green module uses this fused graph to clean the image, producing the final denoised depth map on the right. Moving on to the numbers, this table really quantifies the performance. It compares GIGA-ToF against both single-frame and other multi-frame methods on the synthetic DV-ToF dataset. Okay, 2 key metrics here are mean absolute error, which is the average error in the final depth map, and temporal endpoint error, which measures the flicker between frames. For both of these, a lower score is better. And looking at the results, GIGA-ToF achieves the best scores in every category, significantly outperforming all previous methods in both accuracy and that crucial temporal consistency. And to really see what that lower temporal error looks like, this next set of visualizations is perfect. These are called XT slices. Okay, so imagine taking a single horizontal line of pixels from the video and stacking them up over time. The vertical axis represents time, so perfectly smooth vertical lines mean no flicker. Looking at the ground truth, you see that ideal smoothness. But the other methods, WMF and MTD-net, are incredibly noisy and jagged. Then you see the GIGA-ToF result. It's dramatically cleaner and much more stable. Okay, so performing well in synthetic data is one thing, but the real test is generalizing to messy, real-world data. And that's what this figure shows, using a Connect V2 sensor. What's crucial here is that GIGA-ToF was trained only on synthetic data. Looking at the other methods, they either blur details or introduce major artifacts. But the GIGA-ToF result is incredibly robust. It cleans up the noise while accurately preserving the fine details of the bookshelf and the wall. This really validates its effectiveness in practical, real-world scenarios. So to wrap things up, the key insight of this work is really elegant. Instead of just blending depth values from different frames, which gets messy when things move, GIGA-ToF focuses on the underlying graph structure, that network map of pixel relationships, which stays consistent. This approach, which is mathematically grounded in a method called maximum a posteriori estimation to find the most probable clean image, allows the model to dramatically reduce both errors and that annoying flicker between frames. The results really speak for themselves. That's all for this week's AI Research Roundup. Thanks for tuning in.